name is Andrew, and today I'm going to be presenting on PIEZO1. PIEZO1 is a pressure sensor in red blood cells that is located on the plasma membrane and is used to both regulate and detect the pressure in the blood. It acts as an ion channel, and when a change in pressure occurs outside of the cell, it will allow calcium 2+ ions to enter the cell. This then leads to reactions that can equalize the pressure. This protein can have a mutation at the position 2456, where an arginine is switched to a histidine. This is called the R2456H missense mutation. The primary structure of this protein at the affected area can be seen here on this alpha helix diagram. We start with glycine, and then we move to originally arginine, and then we have a valine, and then a phenylalanine, and then a lysine. This alpha helix itself is not the primary structure, but the secondary. And once we have the mutation, the R2546 mutation, then that arginine will be switched to a histidine, which then switches the order of the amino acids, thus affecting the primary structure. The secondary structure, being the helix itself, will not be severely affected because the protein that changes out will not have different capabilities of hydrogen bonding, at least not significantly. The tertiary structure can be seen in this larger model, where this part is going to be the channel opening. This is the affected area, with this being a marker of where the arginine would have been swapped out. And this is the blade of the protein. The quaternary structure would not be severely affected because it is essentially just 3 of these tertiary structures combined to make this sort of rotary blade shape. The affected mutation would occur around here. So what does this mutation do? Well, the mutation causes a longer latency in the opening and in the closing of the channel. So when you switch out this arginine for a shorter histidine, that makes it so it does not reach as far out from this column or this ion channel gate, and so it cannot interact as easily with the environment and tell this channel when to open and close, which means it takes a little bit longer to do so. It can still do it, but it takes longer for it to sense things. And that means that it can take a little bit longer for this channel to open up when there is actually a pressure that needs to be sensed. It also means that when it does open up, it doesn't close on time every time, which means more calcium 2+ ions can enter the cell when they're not supposed to. This then leads to a cascade of reactions due to other proteins, which leads those ions to be expelled at such a rate that osmosis actually leads to higher osmotic pressure leading out of the RBC, which means water leaves it and it shrivels up. The model has a few limitations, the first one being that the residue interaction in all 3 of these models is not really shown because it would be difficult to do. So there's interaction with hydrogen bonds between these amino acids up and down that help to keep this alpha helix in shape, and that's difficult to represent on a 3D model without it getting too cluttered. Another limitation of this model is that the full volume of the protein is difficult to display. For instance, these arms would be a lot more fleshed out in the actual protein. By the way, this is it being seen from the top, so if you're looking at the cell from outside, it's not this thin in the real model. But in order to be able to see all these arms of it, and also see where the channel meets the center, I didn't want to clutter it up too much and show the full volume because, again, that could make it harder to see key details. A further limitation of this model is that the changes in shape are difficult to visualize at this level because there isn't a huge change to the 3D structure of this protein when you switch out arginine for histidine, because arginine is a charged polar amino acid and it's hydrophilic. Histidine is as well. It's also positively charged, which means you're not really going to see a huge change in the 3D conformation. But you will see a different change in the size of the protein. So while you may have had one that stuck out to here, you will now have one that sticks out to here and is less able to interact with the environment.